In this video, we're going to talk about phase change. So what happens when heat is applied to a material to the point where it changes from one phase to another. So that's one of the ways that, or one of the responses that materials can have. And so phase change can go in either direction. So it can go either, for example, for solids to liquids, or it can go liquid to solid. It just depends on what's happening with the energy, with the heat. So think about an example of a solid liquid phase change. I mean, the one that most of us are familiar with is water and ice. So ice to water or water to ice, all right? Now, that's the most common solid liquid phase change that we experience on a common basis. The solid liquid phase change, it occurs at the freezing point or melting point, depending on which one you're doing. So freezing point if we're going liquid solid, or melting point if you're going solid liquid. And both of these are the same temperature. A lot of people think that they have to be a different temperature, but for example, for water, when we hit 0 degrees Celsius, for the temperature, for the average kinetic energy, that's when we're going to go from a liquid to a solid. Or if we get to 0 degrees, just above 0 degrees Celsius, that's when we're going to go from solid to liquid. So it just depends on which direction you're going. Oops, sorry. So as far as the phase change goes, again, this occurs when you're adding or subtracting heat. So you're going to get this to occur. Now, we are already familiar with the fact that you're not going to instantaneously turn an ice cube into water, right? You add heat and the whole thing just doesn't go poof and turn into water. And that's because you have to increase that internal energy, increase the kinetic energy of all of the molecules in order to get them to go from solid to liquid. And so you're increasing the temperature, you're increasing the average kinetic energy, but you end up having to increase the kinetic energy of all of the molecules in order to get all of the material to phase change. So this is just taking a look at how that energy is working. So if we're going from solid to liquid, we're going to melt, and the material is absorbing energy. You have to add heat to it, which makes sense. We get that. And then freezing, this one's a little harder to think about. When we freeze something, when something freezes or goes from a liquid to a solid, it's going to release energy. So when we think about water to ice, that one's a little harder to think about because we have to put it in the freezer or whatever. But whenever any material goes from liquid to solid, it's going to release energy. And so think about, like, for example, if you're working with wax, and you've melted the wax and now you're letting it cool. Well, you're letting it cool, but it feels warm as it cools. And that is because it's letting out the energy, it's letting out the heat as it cools and turns back into a solid. So the next phase change is liquid gas. So we keep going up. And if you think about it, if you think of examples, again, if we're thinking water to water vapor, but there are other ones, lots and lots of other liquid gas phase changes. And same thing, liquid to gas happens at the boiling point, and gas to liquid happens at the condensation point. So that's when the gas condenses or collects back to the liquid. And again, same, both at the same temperature. And so back to this diagram, we've got our liquid, we increase the energy, add heat, it's going to absorb that energy and go to a gas. If it can release the energy, it's going to condense and go back to that liquid. So anytime we're going solid, liquid, gas, we are going to increase the energy of those molecules. They're absorbing that energy. For going the other direction, gas, liquid, solid, the energy is going to be released. So we're going to get decreased potential energy in those molecules. There's one last phase change. This one is less common, and that is the solid gas phase change. The one that you're probably the most familiar with here is dry ice. So the carbon dioxide one. So dry ice is frozen carbon dioxide. It's pulled below its freezing point. But the freezing point is well below room temperature. And so if you set dry ice at room temperature, it instantly goes from a solid to a gas. There are other examples of this. For example, mothballs contain naphthalene. That's what gives them their odor. And that is also a solid gas phase change. So it goes from solid to gas. That's why the mothballs disappear over time. The one other solid gas phase change that you've experienced is in your freezer. And that is the ice that builds up on the inside of your freezer, the frost, because the water vapor from the air will freeze to the inside of your freezer whenever you open it. And so that's another solid gas phase change. So there are all of those. And this is called sublimation. No matter which direction it is, if it's solid gas, we call it sublimation. And so if we're back here, so if we're doing solid gas, it skips right past the liquid phase. What happens is you're putting so much energy, so much heat in it, that the molecules just go from here to here. They have enough energy to skip right over the liquid phase. So there is that information just kind of summed up in one table for you. So the last thing in this section that I want to talk about is some special things that are related to these phase changes. So the first one's evaporation. And the thing is that a lot of people think about evaporation and they only think about it related to boiling. But the thing is that evaporation doesn't require boiling to happen. And again, it's another thing that you're familiar with if you've ever left something sitting out, like a glass with water in it. You know, I've made up salt water for various things and forgot the cup and left it behind. And, you know, if you leave it for long enough, like a week or so, you'll start to form salt crystals because the water has started to evaporate and you get the salt left behind because the salt doesn't go with the water molecules. So again, remember, what is temperature? Temperature is the average kinetic energy. And this is why evaporation doesn't require boiling to occur. Average kinetic energy. And so individual molecules can change phase at any time as long as they have enough energy to do it. So if you have individual molecules that have that kinetic energy to go from liquid to gas, they can do it. It doesn't require everybody in the material to do it. Just those individual ones can go on their own. So if we take a look at these little beakers here, we've got these molecules. They've got their kinetic energies assigned to them. The average kinetic energy is 11.5, but we've got some of them that are up here that have 25. And that's enough kinetic energy for them to escape the beaker. When they escape, that drops the average kinetic energy to 8, and no more molecules will escape until they gain enough kinetic energy to do so. So this is why evaporation is a slow process. If you've ever noticed that, it takes a long period of time. But if you do evaporation in a warmer area, then you can speed up that process. Cooling, this is a cooling process because the energy is leaving. If you think about it, these guys are highly energetic, which means that they are increasing the temperature because they're increasing the average kinetic energy. When they leave, they've dropped the average kinetic energy, which means they've dropped the temperature. And so If you think about when you've used evaporation, we sweat, right? We put water out on our skin. We're using it to evaporate so that it will cool us off. So what are some ways that you can increase evaporation? And there's lots of ways you can do that. One, easiest way, increase the temperature of the liquid. If you increase the temperature of the liquid, you're going to add more energy. So adding more energy will increase the kinetic energy of more of those molecules. They'll pop out and it'll evaporate faster. You can increase the surface area of the liquid. So by doing this, you give more opportunity to those high energy molecules to escape. If there is a small surface area, it is harder for those high energy molecules to get to the surface to be able to make this exchange. So if you have a larger surface area, there's more opportunity for the high energy molecules to get out. You can remove water vapor from the surface. So if you have something that is containing water or any sort of liquid, very often those high energy molecules do escape, but they generally stay right near the surface. And so you can remove the water vapor or whatever liquid vapor it is, and that'll increase the evaporation. How? You can blow on it or put some sort of, blower or wind or something on it, and that will increase the evaporation because it'll blow those high energy molecules away and allow the other ones to come out. The last one, and this is one that a lot of people don't know about or don't think about or realize that's important to know, and that is reducing atmospheric pressure. So why do we care? This is why water boils faster at high elevations. So if you're doing something that requires boiling water, the atmospheric pressure can mess with that because it will boil faster at higher elevations, but the temperature of the water will be lower than it would at a lower elevation. So here in Ohio, we are at approximately sea level, so the water will boil at 100 degrees Celsius. But if you are at a higher elevation, your water will not be at 100 degrees Celsius when it boils. It will be at a lower temperature. And if you're using something that needs 100 degrees Celsius, that can be a problem. So this is something to know if you are doing something that's temperature dependent, because the atmospheric pressure will change the boiling point of different materials. Condensation. This is the opposite of evaporation. So this is a warming process, while evaporation is a cooling process. Condensation is a warming process where the gas molecules return to a liquid state. So when the liquid molecules evaporate, they take their energy with them. When the water or liquid molecules condense, they release their energy, and that's why it's a warming process. So if we think about, well, actually, no, let me go back to here. If we think about it like this, if you take a shower and you get out and you're drying off and you get cold, what should you do? Well, yeah, you could dry off faster and so forth, but what you can do is step back inside the shower stall and be warmed by the condensation of the water vapor that's still in there. I don't know about any of you out there, but this is why a lot of people like myself close the bathroom door, because it traps the water vapor inside the bathroom and keeps it warmer than if you left it open and allowed that water vapor to escape. So evaporation cools you off, condensation warms you up. The last part of this is boiling. So I mentioned that boiling at elevation can be a problem. I want to just talk real quickly about the process of boiling. So what boiling actually is evaporation. It is rapid evaporation that happens beneath the surface of a liquid. So you can see here, apply heat, and you've got little pockets of evaporated water. So it's little pockets of gas that are popping up at the bottom of the pot. So what happens eventually is if you get enough of those pockets to occur, and the water in general has enough energy to hit 100 degrees Celsius, then you're going to get boiling. So the heating warms the water from below, but you've got a problem. Boiling is going to cool the water from above. So you put heat down here, you get your pot finally boiling at that 100 degrees Celsius, and then the energy is going to leave and evaporate the water out of the top, which, remember, evaporating is a cooling process. So when you're boiling something in an open pot like this, you're constantly having to put in heat and lose it because you're evaporating it. So how can you speed up the boiling process? Say you want to get a pot of water boiling, put a lid on top. Because if you put a lid on top, that traps the heat and keeps the energy from leaving the pot and will help you get this boiling faster. This is actually how pressure cookers work. So pressure cookers have a very tight lid on top and hold the pressurized vapor over top of the water and keeps it from boiling. So that way you can get the boiling point of water above 100 degrees Celsius. This is the only way you can get water to boil above 100 degrees Celsius. Just putting a loose lid on it won't work because eventually the vapor will escape. But with a pressure cooker, you are able to actually get it above 100 degrees Celsius because the vapor can't leave and it holds that heat in, that energy in. All right, that is the end of phase change, and the last section is thermodynamics.